Okay, in this lesson we're going to learn a new test called the comparison test. Let's review the tests that we've learned so far: geometric, nth term test for divergence, the integral test, and the p-series test. And we'll try them out on these series. So pause the video and decide which test you would use for each of these series and whether it converges or diverges. So let's look at this one. We look to see if it's geometric, and when we have an exponential like this, that's geometric with r less than 1. So this is a geometric series and it converges. Here we don't have an exponential, so it's not geometric. We do have the p-series test, and p is greater than 1, so the series converges. On this we have it's not geometric. The limit goes to 0, so we know we can't use the nth term test because the limit is 0. It might converge or it might diverge. We can integrate this with substitution, and so we would use the integral test, and it turns out that this diverges. And then here we have an exponential, so that's geometric with a common ratio greater than 1, and this will diverge. Here we have it's not geometric. The sequence goes to 0, so we can't use the nth term test, and with what we know, we can't do the integral test, and it's not a p-series. So here is a series that we would need to use the new test that we're learning today. This is not geometric, but the limit of the sequence does not go to 0, so we can use the nth term test because this sequence does not go to 0, so the series diverges. And here, if we looked at the limit of the sequence is 2. The limit is not 0, so by the nth term test, this series diverges. Okay, so let's think about what the comparison test is doing. And just look at this graph, and we know that here are values of an, the sequence A, and we know that if we add all these values up, the series diverges. So then what can we say about the series when we add up values of B? If we're adding all of these up, and it adds up to infinity, well, then we add all these up, which are larger than these, then it will also add to infinity. So we know that that diverges. All right. And here we have, we know that the series of B converges, and then we see that all these other terms of A are less than terms of B. So predict what this will do, converge or diverge, when we compare it to what's happening in B. So if we add up all of these values of B, they will converge, the sum converges, and here we're adding up smaller numbers, so they must also converge. And try it on this one. Pause the video and answer the next two. So here we have we know that A converges, the series of A converges, and B is greater than A. So what could B be doing? If B is decreasing fast enough, then it would also converge, but it's possible that B does not decrease fast enough, so we don't know. And here we have A is diverging and B is less than A. So if B increase, well, on this graph, B could go up and then come back down. In that case, it would converge, or it could just keep going up, and then it could diverge. So we don't know. And what we just looked at leads to the direct comparison test. So if we know the series A converges and all the values, all the terms of B are less than A, then B also, the series of B converges also. So to show convergence, we have to show that the series that we're testing is less than a convergent series. And to show divergence, we have to show that the series we're testing is greater than a divergent series. So we see that all the terms of the sequence B are greater than the terms of the sequence A. Here we have all of the terms of the sequence B are less than the terms of sequence A. So let's go through some steps. Step 1, and let's predict what we think this is going to do. Let's predict whether it converges. So we see the denominator is increasing fast because it's exponential with a 3 instead of a fraction here. So it looks like it's going to converge. Then we have to compare or choose something that we'll compare it to. So if we think this is going to converge, we have to show that this is less than some convergent series. So let's compare it to 1 over 3 to the n, which is the same as 1 over 3 to the n. And that's a convergent geometric series, so now we can compare. The sequence of the series that we're testing, the sequence terms are always less than the terms of this sequence, and that means the series that we're testing converges. Okay, pause the video and try that one. So let's predict. And we do that by looking at the denominator. Yeah, it looks like the denominator is going to increase quickly, and it also reminds us of the p-series test. So let's predict that it converges. Choose something to compare it to. So we see this n squared, and we should think of this. Because this converges by the p-series test, because 2 is greater than 1, and then compare. We have to show that the sequence that of the series that we're testing has to be less than the sequence of the convergent series. If the denominator is 1 larger, then that means the fraction is less than that. So that means that the series converges. Pause the video and try that one. So we look at the sequence, and the denominator is not increasing very quickly. It's just a linear polynomial. So we would predict that it diverges. Choose something to compare it to, and that's a 1 over n, so let's compare it to the harmonic series. And we have to show that the sequence of the series that we're testing is greater than the sequence of the series that we're comparing it to. And here we have the denominator of this is less than the denominator of this. So that means we have this fraction is greater than that fraction. That's what we need to show divergence. We have to show that these terms are greater than these terms. And when we add these, this diverges. That means this is going to be, all these are above a divergent. These sequence terms are above a divergent series, so this is going to diverge also. Pause the video and try that one. So when we predict, we want to look at what's happening in the denominator. Well, the denominator is increasing, but so is the numerator. So if we compare the degrees of the numerator and denominator, we would end up with 1 over n. And 1 over n would give us the harmonic series. So let's predict that it diverges. And it looks like hopefully we can compare it to the harmonic series. And if we're showing divergence, we want to show that this is greater than this. So before we can say this is greater than that, why don't we write it like this? So if we make the denominator smaller and the numerator larger than this, then that means this fraction will be greater than this fraction. And this is equal to 1 over n. So this shows that the sequence that we're testing is greater than the harmonic sequence. Therefore, the series diverges. That's the end of this lesson.